Okay, we posed this problem. Let's make sure everything's visible. Okay, we pose this problem where we have two waters. Okay, this is water one, this is water two. There's a diameter ratio of, we'll say P for the ratio. I like to use R, but if you got a diameter, you think radius. So R might not be the best choice. So this red with P. The diameter ratio is P, and they have equal lengths. Okay, so the question, what's a voltage ratio? Now you understand this is a situation that we did in lab, right? Week before last, but we haven't formally addressed the whole conduction model, which is what the current chapter is covering. But we set up a lot of it. So got this, and I asked for the voltage ratio, no hints. Okay. People didn't make much progress. But they write stuff down, you know, looking back at notes and stuff. Well, then I said, okay, well, the currents must be. Okay. Still didn't get very far. I said current density is current per unit area. Okay. That didn't quite click. That's okay. But yeah, within a week it needs to click, and hopefully by Friday's lab it needs to click. If not, we'll kind of make sure it does. Okay. And so you probably want to review what we did, the video from the lab. You know, flip through it, see what you understand and what you don't. And of course, lab was truncated because we had to leave early because there was going to be severe weather 12 hours later or something like that. We still got a lot of them. Okay, anyhow, we got current densities, current per unit area, and all that was defined. Okay. So if you don't remember it, well, it's been 10 days. You know, it was new. So be it. Anyhow, your current density is current per unit area. So the next question I ask is, well, which water is going to carry the greater or have the greater current density? So current density is just magnitude of current density. The vector, it's obvious the direction of the vector in this case. Well, the current's got to be equal. The thinner wire is going to have the greater current per unit area. They have to have the same current. This has less area. That occurs in wire two. Okay. Now, what does greater current density tell you? Current density is just a multiple of the electric field and the conductivity and stuff. Okay, it's the same wire, so we don't have to worry about conductivity. It's the same in both of these things. Okay, got the same number of electrons available per unit volume. For copper, turns out I finally looked it up, and it turns out that even though copper has a valence of 2, only one of those electrons makes it into the conduction band. So the number of available electrons is just equal to the number of operators. And if you know the diameter of the copper, the length and all that stuff, you can figure out the mass. You know the mass, you know, using atomic weight. If you know the mass, you calculate the number of atoms, and the Gauss number, so you know how many electrons there are in that wire, which is kind of good. Something you wouldn't have to do. So hopefully I made an impression. It's not difficult, uses common sense, stuff that you know from Avogadro's number and have used in chemistry, as well as previously in this class. Okay. So you got less cross-section area, same current, you got a greater current density. What is it? It controls the current density in a given substance. It's the electric field. The more electric field you got, the more acceleration the electrons have in the direction of, well, opposite the direction of the field's direction in which positive charge is accelerated. So electrons are going to be accelerated in the opposite direction, the opposite of the field. Sometimes that matters. You kind of want to remember that. Again, that's not a difficult idea. Okay, something else is current density, current and field and stuff like that. It's kind of one of the big central concepts, which that's what we want to concentrate on. Okay. Again, greater electric field, more acceleration, they pick up more velocity, pretty quickly run into other electrons or atoms in the lattice. Okay. And I think most often probably other electrons because they're moving around. I don't know, the atoms are there. You can work that out. And that's another thing that's forgot later in the chapter. Point is, to get accelerated, I'll real quick, they hit another electron, bounce back. But there's a net drift in the direction opposite the field. And that drift is what gives you the current. It's a slow drift. If you have a fast drift, pretty quick to melt the copper. Real quick. Yeah. Put too much voltage across too thin of a wire, you get too much electric field. You accelerate the things like crazy before they run into other electrons. And in the meantime, everything heats up because the average kinetic energy per particle goes way up, and that's temperature. And boom. Okay, thin copper filament just kind of explodes on you. Thicker one heats up more gradually than melts. Okay. It's an overall picture. Back to this. What we know, same length, some EMF, got two voltages, one known voltage ratio. We don't know how to get the voltage ratio out of the details, but we do know that the currents have to be equal, which leads us to the idea that current densities aren't going to be equal, which leads you to the idea that the electric fields are equal. Right? Okay, well, it's really bad. Current density is proportional to E. Okay. What can you do with that? Think about it for a couple of minutes. I'm going to ask you to huddle together. See if you can sort this out. If you can, it's a huge step. If you can't, I'll make it for you. If you make it for yourself, you're going to learn it much better. Okay. Didn't get a whole lot of progress. Current density is proportional to the electric field. Okay. So you're going to have a greater electric field here than you're going to have there. So which one's going to have the greater voltage change? Which is the magnitude of voltage going to be greater? One or two? Got a vote for one, got another vote for one. 3 votes, everybody's on. Okay. You got a greater electric field here. how's electric field related to potential difference? Well, electric field measures what? Let's talk about it. You know. Okay, so we didn't make a lot of progress in this. So now when I ask, okay, what are the units of electric field? I get an answer. Okay. Now somebody did say it's potential difference over distance divided by distance. That's right. Okay, so that's a pretty good answer. There's something going on there. That's good. Electric field is force per unit of charge. That's how you have to understand electric field, not in terms of a formula, or not just in terms of a formula. Understand it in terms of units, it's units per coulomb, force per unit of charge. There are a bunch of different formulas for electric field. KQ over R squared. Okay. That's one. It's good for if you're talking about the electric field of a point charge. And you've got a bunch of point charges, just add up a bunch of KQ over R's. R squares. Something there. Okay. And if you want potential, you add up a bunch of KQ over R's. Only works for point charges. You got a distribution of charge, a line charge, sheet of charge. Okay. For strictly symmetric charge, you're going to have to use an integral, Gauss's law. Okay. There's your field in newtons per coulomb. Force per unit of charge. It's AE per unit charge. It's the work done equal and opposite to the work done by the field on the charge. Then joules per coulomb. Okay. So current density is proportional to number of newtons per coulomb. Okay. V is your number of joules per coulomb. How would you relate V to E? Well, if you have a constant electric field, you multiply the newtons per coulomb by the number of meters to get the number of joules per coulomb. Number of meters from here to here is the same as number of meters from here to here, so they have the same length. But because they have the same length. That allows us to conclude this V2. Which one is wrong? V2 is greater than V1. Greater current density, greater electric field, same length, greater voltage. Okay, there's a simple reason. And it's less a cross-sectional area. There's the whole reason. Now, how many times greater is this voltage than this one? Electric field is force over charge, right? Voltage is force times distance over charge, which of course is E times D. Okay. And that's fundamental for capacitor. You just did. If you got a parallel plate capacitor, you get the voltage, Gauss's law, charge density, all that stuff. And you multiply that by the separation to get voltage plus capacitor. Okay. That's how you have the voltage. You get the electric field from Gauss's law, might have said voltage. And get the electric field from Gauss's law, you multiply it by the separation plates, and you got the voltage. Okay. The charge of the voltage is your capacitance. Now, you don't need that for the test, but you do need it to understand some stuff in this chapter. Okay. Now, this is review. This review stuff you're going to be testing on. Okay. Okay, well, try to understand this as deeply as you can. Not just in terms of formula, in terms of look at it and see what's going on. You look at it, you see you got more area here than you have here. You got the same current. Current is a result of the electric field. Current density is a result of the electric field. Multiply that by the cross-sectional area, and you get the current. And certainly this whole region process. The ratio the whole sequence of reasoning, a lot of insight to be gained, both about what you're about to be tested on and about what you're going to be doing from home. Okay, I want to go over the cheat sheet. And some of the stuff I'll write down, some stuff I'll just talk about. First thing you're going to see is I don't give you any formulas. But a lot of this stuff will remind you of formulas. So, for example, I give you rho GH. Well, that ought to ring a bell for you. You ought to understand what rho GH means. And I also give you rho GY. Well, sometimes you use H for the depth of the water, and sometimes you use Y or whatever the fluid is. Okay. And rho G. Rho is what? Rho is mass per unit of volume. G is acceleration of gravity. So rho times G gives you weight per unit of volume. Okay. And you multiply that by the depth. And it gives you force created volume, which is pressure. Okay. So you need to understand that the 1/2 rho v squared, you should all remind you of Bernoulli's equation. Now they're not going to be right next together. Those two expressions are going to be more or less random positions within the document, because I don't want to give you too many hints. In other words, I want you to really understand this for the major quiz, because you're not going to have this for the test. It's part of your test preparation. Okay, give you a major quiz and then a test following soon thereafter. Yeah, one more thing I mentioned about the major quiz. If you don't do well in the major quiz, you will at least get feedback. And if you do better on the midterm than you do on the major quiz, then I'll replace your a bad major quiz grade with the midterm. Let's go the other way. Midterm, you're on your own. No formula sheet, no expression sheet. I call this an expression sheet. Okay. I don't tell you that rho GH is pressure. You should know that. Okay, and make sure you understand the connection as best you can. Okay. And how is change in pressure related to work and volume? Well, one of the introductory problem sets tells you that. Remember, you force that plug of water out by changing pressure, you get a velocity. Well, you really, I expect you to totally understand the introductory problem sets. If you understand that, then you understand that relationship. Okay. I think your text is that relationship as well. Okay. Okay, well, that's the idea. You're getting expressions, you're not getting formulas. I don't give you the Bernoulli's equation, but I give you pieces of Bernoulli's equation right there. Okay. So if you don't remember what the expressions are, now hopefully by the time you really understand all these expressions, you don't need the sheet. Yeah, at this stage with the test coming up within a few days, you probably do in realistically. Okay. And one of the expressions here we have is, well, we have 3/2 kT, which starting with the idea of molecule bouncing back and forth between walls and impulse momentum and the average force exerted and the average pressure and all that stuff. You lead pretty quickly to the fact, if you combine that with empirical results, that's 3/2 kT. Okay, is the average kinetic energy per molecule, average translational kinetic energy per particle at temperature T. Doesn't matter how big, how small, how massive, how the particle is, it's 3/2 kT, which allows you to calculate the average velocity if you know the mass of the molecule. And have to know that. The 5/2 kT takes into account 2 degrees of rotational freedom. Introductory problem sets bring that out, I think, pretty well. The text brings it out even better. But it's fundamental. Okay, now we look at 3/2 nRT. Some people didn't respond very well to that, but 3/2 capital N KT. If you know what N means, and you need to know what N means, it's the number of particles. Okay, so 3/2 capital N K capital T is just N times 3/2 KT, which is N times the average kinetic, translational kinetic energy per particle. And you multiply that by N, you get the total kinetic energy of N particles at temperature T. Okay. So you think of it that way, these things are related. And then 5/2 big N KT would be the total kinetic energy, not just translational, of a diatomic molecule, because it gets to move in 3 dimensions, 3 directions. It's 3 degrees of freedom, and it can rotate about 2 independent axes, which we talked about in some detail earlier. Giving it 5 ways to have kinetic energy, and the kinetic energy splits equally between those 5 ways. We didn't prove that. I'd like to prove that, but we didn't. We want to take the time. Okay. Now, what's the relationship then between the capital N and the little n? It's pretty easy to understand what the capital N is telling you. You know about 3/2 kT and 5/2 kT. Then 3/2 capital N kT and 5/2 capital N kT have obvious meanings. If you understand that N is total number of molecules or particles in a gas. Or in any substance as far as that goes. The little n is a number of moles, and little n is related to big N by Avogadro's number. So if big N is Avogadro's number times little n, Avogadro's number times the number of moles, then how are big R and little k related? Well, 3/2 nRT and 3/2 nKT are the same. Capital N is Avogadro's number times little n. It's not a big jump to understand that K is R divided by Avogadro's number. So you want to think through that, try to understand that whole idea. Okay, now you got stuff about heat here that's obvious. You got stuff about waves that are obvious. Okay, like the F, V, T, capital T and lambda should be F, C, capital T and lambda, as we want to distinguish velocity of propagation from the velocity, changing velocity of the particles in the wave. Okay. Then we got stuff about harmonics, just any standing wave in a medium, linear medium, we have constant speed of propagation, is going to have nodes and antinodes equally spaced. And you take it from that setup to figure out the wavelengths of various harmonics. And that's very straightforward. Okay, a cosine of capital K quantity KT minus omega T is an equation. Could use a sign. We could have a phase angle apply inside that parenthesis as well. But it's one form of the equation of a traveling wave propagating in the positive direction, positive x direction. Okay. And again, introductory problem sets pretty much explain that. If you factor out the K, then you see if you replace X by X minus omega T over K, you have something horizontally transformed. Okay, you have whatever shape here, horizontally transformed in the positive X direction. And that's why this gives you traveling wave, because that horizontal transform, that horizontal shift is proportional to T. The bigger T is, the bigger horizontal shift. So what's here is transformed over to here at a later time. That means it's traveling. Okay. At a speed omega over K. Need to understand that. And then there are 2 statements down there that are going to be on the midterm that I will include them. One says X changes by 1 wavelength, KX changes by 2 pi. If X changes by, if T changes by capital T, which is the period, omega T changes by 2 pi. You got to totally understand in terms of circular model why that is. If you really want to understand the equation of the wave. Then you have 1/2 Ka squared. What's that? Anybody recognize that? If you do, raise up your hand and I'll post the video so you can tell it. Okay. It's total energy for a simple harmonic oscillator. Okay. V equals the square root of T over mu. That's the speed of a traveling wave of attention T and a linear medium of mass density mu. Mu is mass per unit length. Okay. And you see a lot of this, if you take this list against your chapter summaries, you're going to see a lot with some explanation. Okay. The vast majority of it's there in the introductory process. Then you got cosine of kx minus omega t or sine of kx minus omega t. It's just a varying part of that a cosine of kx minus omega t. Multiply either of those by amplitude, you get the equation of traveling wave. And then you got sine of kx sine of omega t, which is standing wave. Again, the introductory problem said hit that. And I think it's in the introductory process. If y of t is your equation of a wave, could be in the form of a traveling wave with cosine or sine of kx minus omega t, or a sine of kx sine of omega t. Be a standing wave. Either way, take either of those and plug it into this formula. And you get a squared over omega squared. Or it's just partial derivative with respect to t. That is the wave equation, as opposed to the equation of a wave. Wave equation is this partial derivative equation, okay? And it's not c squared. Well, okay. These two lines ought to be on one line. Anyway, I misstated before because I wasn't thinking, but the partial derivative of y with respect to t is just omega squared times y. Partial with respect to x is just k squared times y. Okay, and this should be one equation. I don't know how it got split in a different line, but it did. And the equation is totally obvious. If you plug either of the forms above that into the equation, which should be second partial y with respect to t equals c squared second partial of x with respect to t. Often the c squared is on the other side with a reciprocal. Either way, it works. That question could be on the test. I could give you an equation and ask you, does it satisfy the wave equation? Okay. The wave equation is a partial differential equation. The equation of the wave goes into the wave equation. Y stands for the equation of the wave. Make sure we understand that. Nodes occur when kx equals n lambda. See what that one means. Cosine of kx minus omega t plus the cosine of kx plus omega t equals 2 cosine of kx cosine of omega t. You can prove that if you know that the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. Just comes right out. And what does that represent? Cosine of omega kx minus omega t represents a wave traveling in the positive direction. And cosine of kx plus omega t, a wave traveling in the negative direction. They come together and they form a standing wave. We did a lot of pictures of that. So you understand those pictures. Okay, well, that's pretty much what you need to know And I'm going to confine it fairly close to that, because we didn't do the MyLab stuff for these chapters. It would have killed you. And I want you to stay alive long enough to suffer through electricity and magnetism. Okay. But there it is. Okay. And I say these are reminders, not rigorous definitions. For the rigorous definitions of the text. And the rigorous definitions include the conditions under which these things apply. Don't be confused with conditions. Don't use equations of uniformly accelerated motion for simple harmonic motion, which you all nailed first time in history on the final last semester. Okay. Don't use Coulomb's law to calculate the electric field between two plates of a capacitor. Use Gauss's law. Okay. Coulomb's law only applies to point charges. The plates of a capacitor are not point charges. You can break it down to point charges, and you have to integrate to find the field on every increment of area here from every increment of area on this plate. Okay. You can do that, at least you will pretty soon, like this week in global calculus. But you really don't want to. It'd be a real can of worms. Okay. Okay. Now the rest of this is much shorter list for electricity and magnetism. We'll talk about it next time, but you should really figure out what each of these expressions means at the most basic level. Level of the unit, level of what's going on with this particle in this situation, level of the entire situation to which it applies. Okay. Now, if you get close to the test, you got to use formulas, make sure you use them right. But you use them right if you understand them, you know what formula to use if you understand them. You don't use the wrong formula in a situation where you need to use them. Okay. So take those words of wisdom for whatever they're worth and proceed. No.